which is good because this is exactly where I started yesterday. So we're in sync. So we're looking for different types of loop invariants. When I started teaching, I said it was an art form, and I didn't know how to tell you to find one. But there's some concrete kind of ones that are useful. And when you have to come up with your own loop invariant, you want to see, well, is it one of these obvious things? And the first obvious thing we're going to do is saying, well, the input is the list of objects, and the loop invariant will say not an action, so we don't want to say I'm reading. It's the past tense. Somehow I have, we are considering first I of the objects, or some I of the objects, but usually the first I. And we're going to pretend that that's the entire input, right? So we're going to ignore the rest, pretend that's the input. And if that's the input, then we should have the solution already, right? We know what the solution would be to the problem if that were to the input. And we're going to have some extra information because that'll help us move along, right? So this hopefully all reminds you of finite state automata, which I was doing loop invariants for this just yesterday. Yes? You get more of the input. Yes. No question, stupid. Anyway, so right. So what is this? What does this do here? Right. A finite automata. It reads the characters of the input one at a time, and you never can go back and look at the input. So at every point, you have to be ready that maybe this is the entire input. So you know, what do you know? You know whether the answer is true or not, and you know some extra information, right? So how do we go forward? How do we take a step? Is obviously you look at more of the input. You look at the next object, and then you think this extended thing is the input. And as such, you have to calculate, oops, where did it go? Oh, I fixed some of the slides, but I guess I fixed it. The solution came second. Anyway, this is the solution for this input, and this is the solution for that input. And given that they're different inputs, they could have very different solutions, right? But presumably, a small change in the input leads to a small change in the output, and we can use the fact that we have a solution here and the extra information to get the new solution, right? Everybody good? And so what do you do to make progress is you consider one more object. And then how do you get the post condition? Well, the exit condition will say that we've looked at all the input. And then so the whole input is the input considered. And then the loop invariant says that we have a solution, in which case we're done, right? All right, so now let's consider an example. Suppose that you've never seen an algorithm for sorting before, and we need to come up with an algorithm for sorting, right? So what's the input? Well, it's a bunch of numbers, right? And so what will the more of the input loop invariant say is consider the first I numbers, and our loop invariant says that we have the solution, right? Well, what's the solution in this case? It's some of the numbers sorted, and those numbers sorted. So do we have, and we don't need any extra information. That's what we have, right? And so in some ways, this is the loop invariant we had before, right? Some of the numbers are sorted. The rest of the numbers are off somewhere, right? And then how do we make progress? Well, you consider the next object, and now this extended thing is the input, so we have to get the sorted of the extended thing. And how do you get the extended solution from the solution we have? Well, you insert you insert the object, right? So it just kind of falls out, right? Everybody see that? We didn't even have to do any thinking whatsoever to get this algorithm. Everybody following this? And everybody, remember, everybody's committed to saying when they don't understand something. So if I'm going along, I'm going to assume you're following it. Yeah? That's our loop invariant. Remember, we don't want to worry about the whole computation, right? Otherwise, that's too scary. So we only worry about one step, right? So we assume that the fairy godmother has given us the loop invariant at the top of the loop, which is they're sorted. And then we just have to, our task is to do one iteration, right? Is that, everybody getting these ideas? Right? All right, so some answers that I've gotten from midterms are each iteration considers the next input. Is that good? Is a loop invariant? No, remember that's an action, right? It tells me what I do each iteration. It doesn't tell me what my loop invariant is, right? I could say we've considered the ith input. Well, what about the other ones, right? We've considered the elements 1 through I. Yeah, and so what? You considered them, right? All right. So we've read the first I objects, and we have a solution for each of them. Yeah. I mean, even what you say sounds, I don't completely like. We don't have a solution for each number. What does it mean? I've sorted the 2 and I've sorted the 8, right? No. You've considered the whole thing as one object and you've sorted it, right? So as said, right? Everybody following that? So here we have a solution for the prefix of elements consisting of, right? So that's what we want. Everybody good? All right, so now let's just do the easiest example ever. We're just looking for the largest contiguous block of ones. Yes? Well, we haven't. This is what we're doing right now. We're going to give an example of some additional information. All right? So we're looking for the largest block of ones. So what you want to say, if we've read that so far, what do you remember so that you can, you don't have to go back, right? So it's like a DFA. What do you remember? Obviously, you're going to remember what is the longest block so far, right? That's the solution. If that was the input, then the solution tells me the longest block. Now, as an aside, anybody know, is this a deterministic finite automata? It's not a finite automata because if I'm going to remember how long this block is, I need more than a finite amount of, I need log n bits of information, not a constant number of bits of information. Put that aside. So what are you remembering? You're remembering the block so far. And what do? You read the next character. We got the block so far. Next character. Right, the next character. Oops. What happened? Our current block became longer, right? So what do? Right? We need to replace it. But can we? How do we know that it got one longer? My loop invariant is telling me I'm remembering the largest block so far, right? And I don't know anything else about the past except what I'm remembering. So do I know that that we have a longer block? Not if you don't remember it, you don't. Right? This is just saying, what am I remembering about what I've seen so far? Right? What I'm remembering is this. So I don't know how many ones I've seen. If I don't remember it, I don't know it. Right? So we have to include extra information. Right? we have to include the extra information of how long is the current block. So that's an example of extra information. And so now what do? Well, we read in 1, we can extend our current, right? We keep extending our current until it's ready to shift forward, right? And, of course, if a 0 comes, then your current becomes empty, right? Because that block, the current block, is of empty size. Yep?
So the loop invariant would be that we read prefix from 1 to I and we know the
And? Yes. Right? Doesn't that make sense? In fact, I mean, if you were writing the code to do this, you would have variables which remember the longest block, and you would have variables which remember how many ones we've seen in the current block. You would remember this, right? And so the loop invariant has to reflect what is it that I'm remembering, right?